This week we have a pretty intense reinforcement learning schedule, especially if you consider starting last Thursday. In a week we're going to cover quite a lot of material. I highly encourage reading the background material from Sutton and Bartow, because there's only so much I can cover in a single lecture. And there's lots of subtleties and details that are quite good to have seen at least once and that are described in the book. Also, I'll cover a few examples, but I'll not be able to cover them completely step by step in all of the cases, which means that it's actually sometimes much better to go over them slowly. And the book also goes over some of these things step by step, which gives you a lot of intuition if you do that. So I highly encourage you to do that. Specifically, the background for this lecture will be chapters 3 and 4. 3 was also listed as background for the first lecture, and indeed I will be basically backing up and recovering some of the material I covered the first lecture to place it appropriately into context, and also because these things are important concepts that we need to make sure that we're all on the same page on. So, as always, to recap, we're doing reinforcement learning, the science of learning how to make decisions. Agents can learn a policy, a value function, and or a model in order to do so. And the general problem takes into account time and consequences. Last lecture we didn't. We basically, well, we did a little bit at the end, but at first we just considered the one-off setting where you take an action, you get some feedback, there's no consequences apart from the immediate reward. So you're able to redo many times. That was the bandit setting. In general, decisions can affect the reward and the agent state and the environment state. In this lecture, I will not be talking so much about agent states and environment states. I'll be talking mostly about states in general, and that is because we'll be making the assumption that these things are all the same for now. We'll violate that assumption later, and I'll come back to that. So we'll just simplify and just say there is a state. And this is both the environment state and the agent states more or less at the same time. So, again, last lecture basically we covered the multiple actions but only one state case. And in addition, we basically assumed there was no model. We did cover model-based reinforcement learning where you learn a model, but we weren't assuming the model was given. In this lecture, we'll go towards the full problem by formalizing the problem of the full reinforcement learning setup, so the full sequential structure. But we'll first focus on a class of solution methods in which we assume that the true model is given. And these methods are called dynamic programming, which you may or may not have heard before, but we'll cover what that means at least in the reinforcement learning context. And next lectures we'll cover similar ideas again, but then we'll get rid of the assumption that there's a true model. So if you don't like that assumption, don't worry, it's only temporary. So we'll formalize the interface. We did a little bit of that in the first lecture, so some of this might feel familiar, which is good because this should start to feel familiar. And essentially it means we'll discuss a mathematical formulation of the agent-environment interaction. We'll basically just formalize what all these things mean, just to have both an intuitive and a formal way to reason about these things. And we call that a Markov decision process, as discussed before. And then we can talk clearly about what the objective is for the learning algorithm, or for the agent if you will. And also how to reach that objective, how to construct solution methods. That's a part that we didn't cover in the first lecture. So, Markov decision processes, they formally describe basically an environment. And for now, as I said before, we're going to assume that this environment is fully observable, which means that the current observation contains basically all relevant information to make a decision and also to make predictions. This is sometimes an unrealistic assumption. If you again think of the robot case where there's a robot driving around the corridor and it maybe has a camera, it maybe only has this camera pointing one way and it cannot see what happens behind it. In that case, you could say that the observation does not fully describe everything you need to know about the environment state. But it's still useful to consider Markov decision processes, even if they don't cover all of these cases, because they allow us to formalize everything. And indeed, they're a very general framework. Because even in the case that I just described, you could say that the observation to the agent might not be the full environment state, but the problem that the agent is trying to solve might still be a Markov decision process underneath. It just might be that you have a limited view. However, in this lecture, we basically assume that you don't have this limitation and that you can basically see the environment state. It's indeed within the framework, and it just means that this is called a continuous Markov decision process, which means that the amount of states that you have is basically a continuum, and also the amount of actions that you have is basically a continuum, but the formalism still applies, and many of the results in the formalism also still apply. Also, even when the interaction is partial observability, then still you can convert this to a Markov decision process. One way was given in the first lecture, where if you think about the full history of interactions that an agent has had with an environment, this is a Markov state, because you can never add more history to it to make it more relevant. That's not a real solution in practice, because this history will grow unbounded, but it shows that the formalism at least applies. And maybe that means that more in general, and indeed this is true, there are ways around partial observable problems. Now, also to tie it back to the previous lecture, bandit problems are basically Markov decision processes, but they only have one state. So there's no sequentiality in terms of the states. There's still rewards, there's still actions, there's still basically the other parts of a Markov decision process. But it's a fairly degenerate one. Okay, so to recap, the Markov property, why are these things called Markov decision processes? A process is Markov if, essentially, as it says on the slide, the future is independent of the past given the present. This is just basically, this comes from the formal definition of the Markov property. It means that the current state is a sufficient statistic. It contains all the information that you need to know. And for a Markov decision process, this basically means that the joint distribution on the reward and the next state, when you condition only on the current state, is the same as if you would condition on all previous states. This intuitively means that if you would know all the previous states, this gives you no additional information about what the next state will be and what the reward will be, which means you don't have to look at them. You can just look at the current state. So when the state is then known, the history may be thrown away, which is very nice. It's very convenient. And this is also, there's algorithms that make this assumption that are quite efficient. And we'll later talk in later lectures about what happens when you can't make this assumption, how you can still get a lot of good guarantees. But for now, we're just going to stick to the Markov decision process, which can then be formalized as a tuple of a set of states, a set of actions. P is basically the probability function that describes your dynamics, and gamma here is a discount factor. The dynamics are sometimes described separately in the literature, where we have a separate reward function and a state transition function, and indeed this is sometimes useful. But you can factor these out, as it says on the bottom of the slide. You can basically still describe these separately if you have the joint distribution. And it turns out in some cases it's actually quite convenient to have this joint distribution instead of thinking about them separately. The reward and the discount together define the goal of this Markov decision process. So they define what it means to be optimal in this process. So to give an example, a concrete one, this is from the book, so you can also look at the example in the book for more detail, or if you just want to grog it more. We're going to consider a very simple setup, which kind of models a robot that cleans cans. And this is a toyish version thereof, in which there are only two states that the robot can see. Either the robot has a high battery charge or it has a low battery charge. And these are the only states the robot can distinguish. Now, in reality, this would be a partial observable problem. But what we're going to assume here, to make it Markov, is that actually the probability of transitioning from one to the other is fixed. So it doesn't depend on your history. This is an unrealistic assumption, but this is just to make it simple and to have a simple example that we can reason through. In this case, the action sets are actually different per state. In the high battery states, there's two actions. You can either wait or you can search for cans. And in the low battery states, there's an additional action to recharge, which basically means that the robot will go to the charger and it will recharge and it will go back to the high battery charge state. You could, of course, if you prefer, think of the interface between the agent and the environment as fixed, that there's, for instance, certain motor controls that you can do, and it doesn't matter in which state you are, you have the same controls available. In this case, you could easily just expand the action set, for instance, in one state where you basically say, okay, there's this action recharge, but when I'm in a high battery charge, that doesn't actually do anything, and then the interface is fixed. In general, you can allow these different actions per state. If you go through the literature, you'll notice that most authors don't make that distinction, and they'll basically just say there's an action set, and it's kind of assumed that this action set is the same in all of the states. Now, the dynamics themselves might be stochastic, and essentially what's happening here, instead of modeling the full problem, where if you can only see whether you have a high or a low charge, that would actually depend on your history whether you would transition from one to the other. Instead, we're just going to assume that it's a noisy transition, where sometimes you go from a high to a low charge, and how often this happens, how quickly this happens, maybe depends on your action. So in this case, the probability of transitioning to a state with a high charge, if you are already in a state with a high charge and you perform the action of searching, is a certain alpha between 0 and 1. Which means that the transition to the low battery states must be 1 minus that, in this case 1 minus alpha, because there's only 2 states. These things should together sum to 1. There's always a state you transition to. In this case, you could define a reward function as well. That could be, for instance, the expected number of collected cans, if you want to have a deterministic reward function. Or you could make this thing stochastic as well, and you could make it, say, the actual number of collected cans, which maybe is, again, you should assume then a Markov function of your state, but it can be stochastic, it can be a random number. But in this case, in the book, the assumption is made that this is a fixed number, and this is a table from the book which basically defines the whole MDP. These are simple functions, so we can just define the functions, the transition functions, the reward functions, by just enumerating. We go over all states, all actions, all possible combinations, and we say what is the probability of ending up in this next state, what is the reward you see along the way. You see that there's this minus 3 reward somewhere there, close to the top. This is when you go from a low charge state and you do a search action, and then you go to a high charge state. Essentially what happened here is that the robot needed to be rescued, and this is a costly thing. So we're kind of abstracting away time, right? We're not saying how long did this take, we're just saying, okay, we were in a low battery state, the robot tried to do search, it got stuck, we needed to rescue it, we need to penalize it so it doesn't get stuck that often anymore, and then the robot could itself learn not to do that, hopefully. Of course, this is only relevant if the probability of that happening is large enough, which in this case is parameterized with this beta. So some of the things here are parameterized, and you could just plug in numbers and you could then solve this problem. We'll talk about how to solve later. Or you could view this as a whole family of Markov decision processes, essentially. Yes?
Sorry, the last one is set low, then it recharges, then it's still low. Didn't we say when it recharges the battery goes high?
Yeah, so if you look at the first 0 there, there's no probability of that happening. But we're still enumerating it, because it's one of the combinations that you should be considering. And indeed, this is typically the case. Many states aren't actually connected. What we do sometimes assume, just because it's convenient for theoretical purposes or for practical purposes, we often assume that all states are at least eventually reachable from each other. But it doesn't mean that there must be a direct connection between any 2 states. So in this case, whenever it's a good question, whenever you're in the low battery states, when you take the recharge action, there's no probability that you'll stay in the low battery state in this simple formulation. And of course, this is one way to look at it, but sometimes it's much easier to look at it more graphically, which is, this is the same problem. And this is kind of using a schematic notation that's used throughout the Sutton and Bartow book, where open circles are used to depict states, and closed circles are used to depict actions. So what you see, for instance, on the left-hand side there's this high battery state, and this goes into a wait action, which then loops back into the high battery state, because apparently in this formulation, there is absolutely no charge on your battery when you wait. But maybe more interesting, on the right-hand side, if you're in the low battery state, if you do a search action, there's 2 things that can happen. So it goes deterministically into the search action dot there, but then there's 2 branches, and these branches are, there's a reward on each of them, and there's a probability on each of them. The 1 minus beta and the beta are the probabilities of each of these branches happening, and the -3 and the R search are the rewards associated with that transition. So here you can see that this is a joint distribution. You never get the reward of -3 when you go into one branch, because what this means is if you go into the left branch, it goes to the high state. This is the when you needed to be rescue situation. Essentially, you were in a low battery charge, you took a risk, you went for the search action, you failed, you got stuck, your battery is depleted, somebody needs to rescue you. But the reward only happens when that happens. It might also happen that you do collect some cans, you get your reward search for whatever that is. Let's assume it's positive, right? You collect some cans, you don't lose some. But this only happens when you are in that transition. So it's a joint distribution. In this case, transitions that can't happen aren't actually depicted. We could, of course, just make it a fully connected graph, but if there's a probability of 0, the arrow is just missing, even though it was in the previous table. Clear? So in the first lecture we talked about returns a little bit, and acting in the Markov decision process will in general result in returns, which is the total discounted reward from each time step onwards. And this is a random variable. It's just all of the rewards can be random because of the state transitions that can be random, because the rewards themselves can be random, and because your policy can be stochastic. And therefore the actions can be random. So it depends in general on the MDP, on the dynamics thereof, and on your policy. And the discount factor, as mentioned, is an important part of this return. It basically defines the return along with the reward function. So the marginal value of receiving a reward much later is discounted. In this case, there's an example. If you wait k+1 time steps, that reward will be discounted with discount to the power k, as compared to when it would happen immediately. If the reward is big enough, this will still be important, and the agent might still pursue it, unless it's too far away, and at some point the agent just stops caring. At least when your discount is lower than 1. In that case, immediate rewards are more important than delayed rewards, is what that means. So what is also sometimes said is that if the discount is close to 0, or when it's 0, then you have a fully myopic or nearsighted agent. And if it's close to 1, the opposite, then you have a far-sighted agent. A discount factor of 1 is typically only used in situations where you know for certain that there are terminations, that there are episodes. In the bandit case, for instance, you could interpret this as being an MDP where each episode lasts exactly 1 step. There are no discounts there because there is no sequentiality. But more in general, if each episode is guaranteed not to last longer than, say, 10 steps, then you might still not need a discount factor because everything's still well defined. However, if your problem can continue indefinitely, maybe you want to trade off the immediate versus the delayed rewards. So this is enumerated here, reasons. So one actual reason for discounted rewards is also mathematical convenience. We'll see an example of that later in this lecture, where we can see that the speed of learning can actually depend on this discount factor. In some sense, your problem becomes easier if you have a lower discount factor. However, if you change your discount factor, it also changes the nature of the problem, and your solution might change. So there's a certain trade-off here. Another thing, so this is related to the mathematical convenience, it avoids infinite returns, at least if the rewards themselves are guaranteed to be finite. But if your rewards are finite, then a discounted sum of them, if your discount is guaranteed to be lower than 1, let's say it's a constant lower than 1, then it's guaranteed that the return itself is also finite. In an undiscounted setting, this is not guaranteed. If you just think of a very simple MDP where you only have 1 state and an action that loops to itself, and you get a reward of 1 on each step, if you would use no discounting, the value of that state would be infinite. This isn't the problem maybe for one specific state, but let's say you want to do control, you want to compare one to the other. It might actually be the case if you don't discount that all of the states look equal because eventually you'll get infinite rewards in all of them. In which case there's no need to act in any different way than random. Yes?
Could you offset by subtracting the value of the maximum state, or the state with the maximum value?
It's a very good question. Can you offset by subtracting, let's say a certain value? The reason I picked a slightly different formulation there from what you were saying, there are algorithms for the average reward case. And if you look at the average rewards, then your value is guaranteed to be bounded even if you don't discount, if the rewards themselves are bounded. And there are also algorithms have been proposed for the average reward formulation of the problem, essentially. But they're out of scope for this course, I would say. Also because we as a community haven't really figured them out yet. Haven't really figured out how best to do average reward reinforcement learning. There are algorithms. We've talked a little bit about an algorithm called Q-learning. There's an algorithm called R-learning, which does something very similar to what you said. It basically subtracts the average reward and then looks at the offset compared to the average reward. But these are a little bit less well understood, in short, and less commonly used in practice as well. Doesn't mean they're a bad idea. It might be a good idea. Okay, so as I said, it's important to note that the reward and discount together define the goal, and that when you change your discount, you might be changing the goal. Now, we talked a little bit about a value function as well in the first lecture, so let's just recap that to be sure that we understand. The value function of a state is just the expected return. I say just, but you have to be careful here because the expected return, of course, depends on the MDP, but also on the policy, so we have to make that explicit in the notation. I hope I didn't forget it anywhere on the slides. The return itself can be defined recursively because the return is just a accumulation of rewards. So one thing you could do is you could take the first reward and then you could look at the rest of the return and just still call that a return, which is what I did there in the second equation. But if you take the expectation of that, the expectation of the next return is essentially the value of the expected next state. I actually said it wrong there. It's not the value of the expected next state, it's the expected value of the next state. Because these things might not commute. So one thing that happens there, which might be good to note, is the first equation conditions on being in state ST and on policy pi. When I just put a pi there, I mean any action that is ever selected is selected according to this policy pi. Pi always denotes policy. In the second equation in the same block there in the middle of the slide, I more explicitly said AT is selected according to the policy. This is because I plugged in the value function, so the other actions are no longer in here. They're basically abstracted away within the definition of the value function at the next state. One thing we can now do, and somebody asked this question as well in the first lecture, we can write it down explicitly using sums, because we could basically just enumerate, as we did before in the table, all the possibilities, starting with the actions, and we could look at the probability of selecting each action. That's what the first part means there. The summation over A is over all the actions, and pi is the policy, and pi A given S just means what is the probability of selecting that action in state S for each of these actions. Then we also sum over all possible rewards and over all possible next states, and we look at the joint probability of these things happening. And then we just get the value of that reward plus the discounted value of the next state. And by definition, this is the same as the equation before, where you maybe noted or maybe even object to the fact that I sum here over things that might be continuous. So feel free wherever you want to replace each of these sums with an integral. For instance, if you want to assume that rewards don't come from a finite set, but they can take any, say, real number, then you might want to replace it with an integral, but the idea behind it is the same. Now, this recursion is a very central and important thing within reinforcement learning. So it's good to understand it, and we'll see versions of this throughout this lecture. Sometimes it's more convenient to write down the explicit form with the summation. Sometimes it's more convenient just to stick with the expectations. But whenever you write the expectations, it's good to be aware what you're actually conditioning on, what you're not conditioning on. Yes, there was a question.
For the sum form equation, what is the first pi A given state? What is that
Yes, a good question. What is this first pi a given s? This is our policy, which in this case I'm assuming can be stochastic. In the simplest case, our policy will deterministically select an action in each state, like one specific action. In this case, this sum basically just becomes an indicator that only selects that action. The pi a of s in that case will be 1 for that action and 0 for all the other actions. The formulation as I wrote it down here is more general, and it allows you to have a stochastic policy where there's actually a probability of selecting many different actions. An example of that is the epsilon greedy policy that we discussed last time, where there's an epsilon probability of selecting uniformly across all of the actions, and there's a 1 minus epsilon probability of selecting the highest valued action according to some estimates that you have. In this case, there's no estimates yet. This is just a definition. Yeah.
Doesn't the sum of the probability, the sum over A of all the different probabilities of choosing all the different A's given S, isn't that 1?
The summation, yes, it is. The question was, does this sum over the probability sum to 1? It does. So this is essentially a weighted sum. It's a weighted average of the things that come after. But note that the things that come after do depend on this A through the probability on the reward in the next value, next state. So you can't pull it out even though it sums to 1. It's a very good question. Thanks. So we can do the same trick using state action values rather than state values. So this is more or less the same slide again, but there's a few little extra nuggets. So first note that the first equation up there now conditions on both a state and an action. We're basically just saying we're still going to look at the expected return, but we're going to commit a little bit further on. We're going to commit after the action rather than after the state. And this means that this should also appear on the left-hand side. And this gives us a Q value or an action value, which we can again roll out. But the first step I rolled out there, I actually stopped slightly short. I only look at the value of the next state. I don't have an action there yet. This is because of the definition of the return. This is perfectly valid. And we could just stop there. But what we could also do, we could go one further and we could also consider the action in the next state. Now, if this action is selecting according to the policy, which it would be, then these things are equal. And that's denoted there at the bottom, where the value of a state is equal to the weighted sum of the state action values, by definition. And this is maybe most apparent if you just look at the first, not the very first, not the definition, but the first equation, where there's a recursion of the Q on V. If you consider putting the summation over the policy before this, then you basically get back this equation. So this is by definition true, but that means that we could also write this down recursively only in action values, which maybe is quite obvious if you think about it, because essentially one way to think about this is that we're not considering the state to be the primary thing here, but we're considering just the combination of a state and an action to be the primary thing. And then you could do the same trick that we did before, where the value of the previous state action value is associated to the value of the next state action value through a recursive Bellman equation. Note that now the summation over the policy is all the way at the inside rather than all the way at the outside. And this turns out to have some implications sometimes for some algorithms, making one easier to use than the other. Now we can also just write this down fairly condensedly using matrix notation if there's a finite set of states especially. So what this equation here means is the same as what we had before. There's nothing changed here, we're just writing it down differently. And the way to interpret this is that this V, this bolded V, is a vector that contains the value for each state as its element. So there's a finite number of states, let's say 10, then this is a vector of length 10. And this vector will be equal to the reward vector These are the expected rewards under the policy that we're considering. So all of this is policy conditional. And this bolded P is called the transition matrix. It depends on the policy, and in fact, this is a definition, so I probably should have added the policy to V as well, because V itself also depends on the policy, similar as before. And essentially what this means is you can see now these transitions, you could see this as a mapping. You map the values at the next state. You get those by mapping the values of the previous state through the transition matrix. I'll just I don't expect you if you're not like believing that immediately or seeing it immediately, that's fine. That's okay. If you just bear with me and believe that this is true, this is exactly the same as the equation that we had before, but just written differently. The summations are just written down as matrix notation rather than explicitly. So why are we going here? Well, it gives us our first solution method. Because essentially, this is just a linear system of equations. This is already true before. If you have a finite number of states, we just had an equation there that related the value of one state to the value of potentially all of the other states. But still, if it's a finite number of states, it's a linear system of equations that we can solve. And one way to solve that, and this is why we went to matrix notation, is in this case it becomes very clear how to solve it, because you can just manipulate the matrices in such a way that you can write down the solution basically in one go. And the way we do that is we get all the values to one side, and then we just multiply with this matrix in front of the value, which is the identity minus the discounted transition probabilities. We multiply both sides with that, and then we get something on the left-hand side which is just your value, and something on the right-hand side that doesn't depend on your value anymore. So this is a non-recursive definition of the value. And if you know your transition probabilities, if you know this matrix, if you know your discount factor, and if you know the reward vector, then you can just compute this. I say just, but this is not actually that commonly used in practice because it can be computationally bothersome. And it also doesn't allow you to focus your compute. And we'll talk about that later, but one way to think about that is that in an MDP there might be certain states that you basically never end up in. States that are basically irrelevant to any prediction problem that you might want to do in that Markov decision process. This doesn't care or doesn't know about that, and we'll try to solve that. Which means that you're basically spending compute on states that you might not care about. In some cases this is fine. If your system is small enough, right, maybe this is a good way to just solve it. But if your system becomes bigger, if you have millions of states, then this becomes unwieldy, of course. Or even smaller than that, it typically does. Now there are other methods, iterative methods that we'll discuss. The one that we'll cover in this lecture is dynamic programming, and then in later lectures we'll cover Monte Carlo evaluation, which uses sampling, and temporal difference learning, which uses ideas from both dynamic programming and from Monte Carlo sampling. And they tend to be much more efficient in very large problems, and especially Monte Carlo and temporal difference methods also extend much more easily to the function approximation case, where there might be infinite possible states, or almost infinite. Let's think again of the robot with a camera input. So another thing that's maybe missing here, this is just for the prediction case, which means that we're evaluating certain policy. This was the Bellman equality equation, or sorry, the Bellman expectation equation, sometimes called, which was this one that we discussed. But this just defines what the value is for a given policy. But that's not actually what we're typically after. We want to optimize. Now the optimal value function can be defined in terms of these values by maximizing over the policy. It's very easy to write that down, it's very easy to say it. It's not that trivial to actually do it, because how do you even reason about maximizing over policies? Because policies are functions. They're functions from states to actions. And there might be many of them, even in small MDPs, there might be many ways to map your states into actions. They're basically a combinatorial explosion of ways you can pick different actions in different states. Because each combination of picking a different action in one state might lead to different values all over in the Markov decision process for all other states. All these things are interrelated. However, it's good just to note it exists, we can define it, and this is the optimal state value function and the optimal action value function, which are very symmetrically defined as just maximizing over these policies. These optimal values, they give you what the best possible performance is that you can get in that problem. They don't tell you how yet, but they do give you what that is, and then the Markov decision problem or process can be considered solved when you find these values. So just a little bit of terminology. Estimating the value of a certain policy, either using state values or action values, doesn't matter. We call this policy evaluation, and sometimes we call this prediction, because essentially we're making a prediction about what happens when you follow a certain policy. Prediction, of course, is maybe a more general term that's used for other things as well. It's a bit overloaded, but you'll see it sometimes in the literature. Estimating the optimal values, on the other hand, is sometimes called control, because these can be used for policy optimization. Essentially, if you have these values, it's very easy to do the optimal control, to find the best possible policy. Of course, both of these are prediction, in a sense. One is predicting the value of a given policy, one is predicting the value of the optimal policy. But there's just this terminology that is used that is associated to these things, which is good to be aware of. Now this means that there's actually 4 Bellman equations, or actually that's not implied by the previous, but there are 4 different Bellman equations. If you just look at the first 2, the first one we covered before. This defines the value of a certain policy for all states. The second one defines the value of the optimal policy. And this is done by maximizing over the actions and then bootstrapping using that same value. This may not be immediately obvious, and I encourage you to read the chapters of Susan and Bartow, where this is also more step by step laid out. But this is a known equation that is known as the Bellman optimality equation. All of these are sometimes called Bellman equations, and then the first one you could call maybe a Bellman expectation equation, and the second one you could call Bellman optimality equation. And then there's those counterparts for the state action values. Where similarly, there's a typo. The final Q there, behind the max A, that should be Q star, not Q pi. I'll fix that before I upload the slides. So these are recursively defined in terms of themselves. And you can show that there's no possible policy that has a higher value than the value given by this definition. That's what you can show. That means that the policy associated with these things is the optimal policy. Especially for state action values, then the policy is very easy to get, which I'll cover later. But essentially you just pick the highest valued action in every state. Now there's equivalence between these state values and these action values. I already covered the first one, which says that the state value for a certain policy is actually equal to the weighted sum of the action values, where you weigh by the policy. Essentially, we're just conditioning. We're conditioning either on only a state or a state and an action. But when we do that, we have to correct for how likely it was to select each of these actions. The optimality equations, or the definitions of the values for the optimal values, are similarly related to each other, but the summation over a policy is replaced with a max. We select the highest valued action, and this will give you the optimal value from that state. This is maybe obvious in hindsight. If you believe that the state action values are indeed the optimal state action values, then what's the highest possible value you can get in the state? Well, just pick the highest one. And it indeed follows also from the definitions of these that this is true. This means that especially if you have a model, as we'll discuss in this lecture, then these things are somewhat interchangeable, because you have these options of first estimating state action values and just picking the highest valued action, or you have the option of estimating the optimal state values and then just planning one step ahead and then selecting an action. That requires you to have the true model, but that's the assumption that we were making here anyway. In practice, a lot of times when we want to do control, we use these state action values just because it's very convenient to be able to pick according to these values. So another way to talk about optimal policies is to define a ordering of a policy, so that we can simply write a policy is better than the other policy. Well, when is a policy better than the other policy? This is true if the value of that policy is at least as good as the value of the other policy in every state. So in both of these cases, it's kind of important that this is a greater or equal than. These correspond to each other. A policy is considered greater or equal to another policy if it's at least as good as the other policy in all states. And then there's a theorem that for any Markov decision process, there exists such an optimal policy that is better or equal to all other policies according to this ordering. And all of these optimal policies, if there are multiple, there might just be one, but there might be multiple optimal policies, achieve the optimal value. There's only ever one optimal value. This is uniquely defined, but there might be multiple policies that attain that value. One way to very easily understand that is if you have an MDP in which all the rewards are 0, it obviously doesn't matter what your policy is. So all policies will be optimal, but there's still one optimal value, which in that case is 0. So if we write down the optimal policy, if we denote that by pi star, then we can basically say, okay, what is the value of that pi star? And this turns out to be exactly that v star as defined by the Bellman optimality equation. These things are the same. So sometimes people might also say that v star is just a shorthand for v of pi star. Both of these are true. So how do we find such an optimal policy then? I already mentioned this. So you can just maximize the optimal value function, state action value function, if you have that. The hard part then becomes finding that. There is always a deterministic optimal policy. And this is the case because if there's multiple actions that maximize, you can pick arbitrarily. So you could pick randomly amongst the optimal actions. Or you could just pick one, pick say the first. But if you pick the first, this will become a deterministic policy. This is only true for Markov decision processes. If you have a process that is partially observable, it might actually be optimal to behave randomly, because you might not be able to know exactly what the state is, and in that case it might be more helpful to not commit fully to an action. But we'll talk about that again later. So the only point here is that it's easy to get the optimal policy from the state action values. But we still haven't talked about how to solve. And it turns out this is a little bit harder. Because, so previously I gave you one solution, but this was only for the prediction case, for the predicting a value of a policy, and that's a linear system of equations. But the Bellman optimality equation has this max over the actions. This means that it's nonlinear, and you can't do the same trick. It's not a linear system of equations, it's a nonlinear system of equations, and that's typically harder to solve. So what we typically do is we use iterative methods. Rather than trying to write it down in one go, rather than trying to find an analytic solution which may not exist, instead we're just going to iterate our way to the solution. And if we use models, as we'll do in this lecture, this is called dynamic programming. And I'll talk about value iteration and policy iteration, which are two ways to get towards the optimal policy and eventually find it. And in future lectures, we'll talk about the methods at the bottom, which use samples rather than the true model. But otherwise use similar ideas. So I found this to be a good quote. In terms of what does dynamic programming mean, where does it even come from? I'll just read it from the slide. In the 1950s were not good years for mathematical research. I felt I had to shield the Air Force from the fact that I was really doing mathematics. What title, what name could I choose? I was interested in planning, in decision making, in thinking, but planning is not a good word for various reasons. I decided to use the word programming. I wanted to get across the idea that this was dynamic. This was time varying. I thought, let's kill two birds with one stone. Let's take a word that has a precise meaning, namely dynamic, in the classical physical sense. It is also impossible to use the word dynamic in a pejorative sense. Try thinking of some combination that will possibly give it a pejorative meaning. It's impossible. Thus, I thought dynamic programming was a good name. It was something not even a congressman could object to. So I used it as an umbrella for my activities. This was by Richard Bellman. I slightly paraphrased just for conciseness. The point here is that it's a kind of a weird name for a process that's actually not that complex. And some people, they get confused by this name, especially later on when programming more or less started to mean what we also might call coding. Whereas in the past, in a more mathematical sense, you'd have things like linear programming, which was more about algorithms and how to solve things. And dynamic programming is programming more in that sense. But still, dynamic programming is not a very intuitive or informative name for what the process is. So don't get thrown by that. It's basically by design. It was meant to obfuscate, maybe more. So we're just going to stick to that. So there's a simpler definition in Sutton and Barta, which basically just says dynamic programming refers to a collection of algorithms that can be used to compute optimal policies given a perfect model of the environment as a Markov decision process. And we'll discuss several dynamic programming methods to solve Markov decision processes, all of which consist of two important parts. One is the policy evaluation part, and one is the policy improvement part. In some cases, these parts are kind of intertwined, as you'll see, but these are the two important things to keep in mind, which correspond to what we were talking about before. So this is a good break point, so I wanted to stop here for a moment because this has basically been more or less definitions up to now, just to make sure you're on board, with the one exception of the matrices where we solved one thing. But otherwise, we haven't really talked about solution methods. So I wanted to take a 5-minute break and then I'll talk about dynamic programming to solve these MDPs. So first, we'll talk about policy evaluation, which just means to estimate that value that we were already talking about before, the state value to start with. I already gave you one solution with the matrices, but now we're going to talk about a different way to come to the same conclusion. And the benefit of this way is that it'll also apply later on when we try to apply this to finding optimal values. But for now, we're just talking about estimating the value of a given policy. So pi, you can consider given for now, and we're just estimating that value. So the idea is quite simple. We have this definition here, the Bellman equation, and this is something that is by definition true, and as I said, it's actually a system of linear equations that you could solve. But the idea of dynamic programming, or at least in this case of the policy evaluation algorithm, is to initialize a first guess, v0. For instance, you could initialize the value for each and every state to be 0. And then we're going to iterate essentially this equation. We're going to assign values, which we now subscript with a k rather than a pi, to indicate that this is an estimate at that time. And the way we're going to assign that is we're basically going to take one step, an expected step using the true model, and we're going to bootstrap, that's what this is called, I'll repeat that later, on the value at iteration k, the previous iteration at the next state, and we're going to use that to find new values k plus 1. Now, a first thing to note here is that if this operation, this is a well-defined algorithm, right? You can do this, you can each time update for all of the states. Just think of it as happening for all of the states at the same time. You could just apply this update and get a new vk plus 1. Now, the first thing to note is that if it happens that your values didn't change because of this update, then by definition you have found the true values. That doesn't tell you that this will happen, but it tells you that if it happens, that you found the right values. It might be less clear that this actually goes in the right direction, that you'll find the values eventually. So it's useful to step through that, and what I have here is essentially a short proof sketch that this is a sound algorithm. So the question here is, does this converge? When I say converge, I mean, does it eventually find the true values? And the answer is yes, under appropriate conditions. And one such condition that helps it converge is when your discount factor is lower than 1, which is what I use here in the proof sketch. And I'll step through this. And the ideas are simply to pick the maximum gap between the value at the iteration k plus 1 and the true values where I maximize over all states. I could have picked different things, and I think the book has a different version of this, but this is one way you could do that. And then the first thing that we do is we just expand the definitions. So the definition of vk plus 1, as given on the previous slide, is essentially the expectation of the immediate reward plus the discounted value at the next state according to the values at iteration k, the previous iteration. That's what the first line says there. And then there's a minus part, which is the true value that I've expanded, which is also defined as the immediate reward plus the discounted value at the next state according to the true value. That's by definition of the Bellman equation, this is true. But then we can note that there's an expectation there, it has a reward, but the expectation is in both cases over the same things. It's conditioned on the state. There's an expectation of the reward, conditioned on the same policy, because we're considering a certain given policy. That means that these rewards cancel, they just disappear. It's the same thing minus the same thing. The other thing I did there at the second equality is I also put both of these things into the same expectation, which you can do because the expectation is about the same things. So I've just got rid of the reward and just wrote it down slightly shorter as one expectation rather than two different expectations minus each other because the expectations are over the same things. Now what's left here is the discounted value at the next state according to either the value function at iteration k or the true value function. But the discount factor, we've assumed is smaller than 1. We can just pull that out. It's just a number. We can pull that outside of the expectation. We can also pull it outside the max because it's just a number. Which means we now have a discounted max over all states of the difference between the expectation of the value at the next state minus the true value at the next state. And at the final step, I basically got rid of the expectation. Now why can I do that? That's because this expectation inside, at the previous step before the inequality, is basically a weighted sum over states. But the weighted sum over states, you could always just pick the max, and then you get this inequality that the difference between that is smaller or equal to. There's a different version that shows why these things converge in the book. I encourage you to look at that one as well. But what this means is that all the way there at the beginning, we had something, and all the way there at the end there, we have something that looks very similar, but it's the difference at the previous iteration times this discount factor. Now what happens if you apply this again and again, because the discount factor is smaller than 1, this means that this difference will go to 0. And that implies what's on the bullet point there, that in the limit, if you iterate this over and over again, you find a true value function. Yes?
Can you repeat why the last step when you get the inequality is true?
I hope it's true. Why the last step is true. My argument that I just gave is that the expectation here basically just implies there's a weighting over states. But if you look at the weighting over states, and the weighting is the same in both cases. So we have a weighted average of states on one end, of state values on one end, a weighted average with the same weights of state values on the other hand. And the claim here is that the difference between those two is always going to be smaller or equal to the difference of the maximum gap there, which is what the final thing defines. In worst case, there's an equality, which is fine because we still have the discount factor. So we're still converging even if that final step is an equality. In general, it might even be a little bit faster than that. It might go down a bit faster. So this is to give you an intuition. It also shows you something that I mentioned before, is that the rate at which these algorithms find the optimal solutions might depend on your discount factor. This makes intuitive sense as well, because if your discount factor is high, this means that you're looking further into the future. So in some sense, this should be a harder problem to solve, because you have to take into account longer delays in potential rewards that you might receive. And this is kind of in general true, that if we set the discount factor higher when we model a problem, it tends to be a harder problem to solve. So this doesn't cover the finite horizon case. This basically covers the the continuing case, where we have a discount factor, maybe we have no terminations. You could make a similar argument for the finite horizon episodic case, where there's always a limit to how far you can go. Maybe there's deterministically going to be a the termination within a certain amount of steps, or maybe just stochastically you terminate sufficiently often. And then even if you don't discount, you could still show that these things converge. But the argument there is slightly more complex. The easiest one to show is with the discount factor. Okay, so what does that look like? Let's consider a very simple setup. This is a grid world. And the axes are just up, down, left, right. We've seen similar things before. And let's assume there's a -1 on each transition. And there's one terminal state, which is basically in two places. This is how Rich likes to formulate these things. If you enter one of these shaded corners, your process terminates. This means there will not be a next state. So what you can then do is you can apply this iterative procedure, which we're going to apply on all of the states at the same time. We're going to apply all of the state functions at the same time. And the policy we're conditioning on, so the policy we're trying to evaluate, we've picked the random policy, which is depicted here on the right-hand side as just having these arrows pointing everywhere. This means that you are equally likely to go in each of these directions. In addition, we've picked an initial value function, just arbitrarily, to be 0 everywhere. So at k0, before the first iteration, if you will, all of the values are initialized at 0. What we then do, we apply this iterative procedure once. We don't update the values in the corners, even though they're in the picture there, because these are terminal states. They're not actual states that you want to know the values of. They're defined to be 0 in a sense. That's another way to view that, because they're terminal. But all the other states are updated. And at k1, all of the state values are -1. Can someone explain why? Yeah?
Because you went one step in all of them?
Yes. And in addition, so the answer was we took one step in all of them. And in addition, the reward was defined to be -1. So in all cases, we saw exactly one reward, and it was -1. This is exactly true. And then we bootstrapped. We used the estimate at k0 to estimate the value at the next state, which was defined to be 0. So now let's repeat that process. Let's do that again. For all of the states, we're still just considering the random policy, going anywhere. And then we're going to do another step of this policy evaluation. At k equals 2, this gives us a new value function, which has a lot of 2's. So I could repeat the question, but the answer will be because we took 2 steps. And it will be 2 because we're not discounting as well. So the second step, like the second reward, is considered equally important as the first reward. But what we're essentially doing here is we're bootstrapping on the state value estimates. So think of the value, for instance, all the way in the upper right corner there. First it's 0. We take one random step. By the way, if you bump upwards here, if you try to go upwards in that state, you'll just bump back into the same states by definition of the dynamics. But if you take a random action from the upper corner, it doesn't really matter. You just get a -1 and you'll bootstrap on the value of the next state, but the value of the next state is 0 everywhere the first time you do that. So the first time, the value of the upper right state will become 1 after one update. The next time you do that, same principle applies. You get a -1 reward, and you add the value, the current estimate of the value, at the next state you end up in. It doesn't actually matter from this top right corner, it doesn't actually matter which state you end up in. They all have the same value, which is now -1. So the new estimate will be -1 for the reward, -1 for the next state is -2. But there are now also a couple of states that don't have the value of -2. So can somebody explain why? Yeah.
So your current estimate is going to be -1, and then for 3 of the 4 of your actions, you'll get a reward of -1, and for one of the actions, you'll get a reward of 0.
Yes.
So
yes.
the expectation is -1.75. I mean, that's your output.
Yes, this is exactly true. So the only reason this says -1.7 is because we've rounded. But it's actually -75 because there's essentially 3 states the random policy might end up in that have an estimated value now of -1, exactly like you said. We do always get the -1 reward, but then the expected next state value is -0.75 because there's 3 that go to -1 and there's still the terminal state that had a value of 0, which remains at a value of 0 always because it's a terminal state. So now you see this discrepancy between the states that are closer to the terminal states and the states that are further. And we can repeat this process because this is still just a very rough estimate of the value. But we can repeat that. For case 3, the values become a little bit different then. We repeat it more. And eventually, when we have infinite iterations, we'll get a value function which has these -14, 20, 22, 18, different values for different states. And these will be the true values for this problem. And the semantics in this case of these values is, this is the negative amount of steps on average that it takes before your random policy ends up in one of the terminal states. Because of the way it's set up, there's no discounting. You get a -1 for each step. So this is just counting steps until termination. So in expectation, from the upper right corner, apparently it takes 22 steps before you hit a terminating state on average. Now there's one thing that's maybe interesting to note, and I'll get back to that as well, is that on the right hand side here, we started up with just depicting the random policy. Now what's happening here on the right hand side is basically completely separate from what's happening on the left. On the left we were just doing this policy evaluation, but on the right what we're doing is we're taking a one-step look ahead using the current estimates and seeing what policy that gives us. So we notice after one step, the states near the terminal states, they already point towards the terminal state. Can someone say why? Why would the optimal policy be, or why would the policy condition on that value function be to go to the terminal state? Yeah?
Because that's the state we can possibly move into with the highest value.
Yes. So condition on doing a one-step look ahead. So I did a fairly long sentence there prefacing the question. Condition on doing the one-step look ahead. In those states, it's optimal to go towards the terminal state. Condition on your current values. In all the other states, just doing a one-step look ahead isn't enough to actually see the terminal state. So in those cases, the policy still doesn't care. If you do another step, you see that more and more arrows start pointing towards the corners. And when we repeat that, actually the policy doesn't change anymore after the third iteration. In all of these cases, they basically point towards the shortest path towards the corners. We didn't ever actually execute any policies. We didn't even consider evaluating this policy. The values there at the left, bottom left, are the values for the random policy. But you could now consider using those values to act. And in fact, if you would do that, it would already give you the optimal policy in this case. Because it's such a simple problem, essentially. However, this points towards something that we can do in general, which is policy improvement. And the example essentially shows that we can evaluate a random policy and then maybe consider changing our policy, and then in that case it would already be optimal. In general this is not true, but we can still apply the principle. We can iterate by essentially picking a new policy, by picking the greedy action according to the action values, according to that policy. So let's assume we've used the process of policy evaluation to find Q pi. In the previous example we did it for values, but you could do the same for state action values. And you could repeat that process, find the actual optimal values, and then you could consider a policy that does better using those values. Now there's a dangling let there that you should just ignore. But the idea is here to iterate that. And what we can then do is take that new policy. We could just, of course, just stop there. We could say, hey, we now have a new policy. In this simple example, it was already optimal. But we could also change the policy and then repeat. We could estimate the value of this new policy. The value of this new policy may, and in general is, different from the value you had before. And then maybe, if you are greedy to the solution to the value of this new policy, again, you can improve yourself. And you can actually show that if you do this way, if you're greedy with respect to your current value estimate, then the actual value of the new policy will in fact be better than or equal to the value of the previous policy. I don't give a proof here. Ignore the dangling let again, but this is true. So there's an intuition here, which is not a proof, just an intuition. But let's assume that at some point we did an iteration of this. We had a certain policy, we evaluated this policy, we have a certain value function, and then we pick a new policy that is better according to that value function. This policy we depict as pi new, and now we consider what is the value of that policy. And let's say we redo the whole policy evaluation to find the actual value of that policy, and now it turns out it's the same. Then, by definition, this equation holds. That in each state, by the way we picked the new policy, by being greedy with the one-step look ahead, you can write it down similarly for the state action values, but we've picked the policy by being greedy with the one-step look ahead. But if the value didn't change, by definition this must be true, which means we found the optimal values. This is the intuition that if this process ends, this process of evaluating and then improving and then evaluating and improving, then you've ended up at the optimal value. And therefore, also at the optimal policy. So the intuition here is that if you improve by picking a greedy policy with respect to your current value function, then either your new policy must be an improvement, which I stated but didn't prove, but this is true, or it must already be optimal. So that's sometimes depicted a little bit schematically like this. You start off with some random value function and a random policy. And maybe the first step that we do is policy evaluation. That's depicted there on the left as this arrow pointing upwards. The line there at the top, you're basically at that line whenever your value is exactly accurate. This is this is just an intuitive picture. There's no formal semantics to these things, but just think of it that way. But if you do the evaluation, it basically means that your value will be exactly accurate after some time. Now you could then greedify your policy. You pick a new policy that is greedy with respect to the current estimates. What this will mean is you will not have accurate values for this new policy. By definition, you've only evaluated the policy you had before, but you've changed your policy and the values may not be the same. That's depicted by the arrow going down, because right now you've greedified your policy, but the value estimates are no longer necessarily accurate. But then you can repeat that process, go back up again, and evaluate this new policy. And the intuition here is that these things actually together they bounce towards a point where nothing changes anymore. But then when nothing changes, and that's what I said on the previous slide, by definition we have found the optimal values. We found something that adheres to exactly the Bellman optimality equation, which therefore means they must be the optimal values. Another way to view that is like here on the right, it's basically the same picture, but we see this as a cycle of things where we have an evaluation step and then we have an improvement step and we just repeat and repeat and repeat until these things bounce back without any change. Your policies no longer change, your values no longer change. This means they must be optimal. Otherwise there could still be change. This process of evaluating and then improving and then evaluating and then improving again is called policy iteration. And it's a very central and important concept within reinforcement learning. And there's many ways to do that. So the principle applies more general than the specific algorithm we discussed. So it's good to keep that in mind. Now, to give another example of that, one a little less trivial than the previous one, let's consider a fairly still simple setting, but more complex than the previous one, where there's two locations which can each hold a maximum of 20 cars. And essentially, the agent here is the rental dealer or the person in charge wants to make money by renting out cars. And the actions are to move cars from one location to the other. This costs you a little bit, in this case -2, your reward is -$2, which basically means it costs you $2 to move a single car, and you can move at most 5, so there's 5 different actions, or 6 if you don't move any. And the reward is otherwise, apart from the -2, $10 for each available car at a location that is rented. We also have to define a discount factor, which we fairly arbitrarily set to 0.9, which means you want to make money now rather than later. The transitions are more interesting in a sense, and it's harder to reason through, which shows that you can use these things without knowing the solution yourself. Because the cars are returned and requested randomly, we assume, according to some Poisson distribution in this case, which is not too important. But the main thing is that these distributions are different for the two different locations. So an intuitive thing, if they wouldn't be different, would be just to balance the cars, and then you should be fine. But if these are different, it's unclear what the optimal solution is. So in the first location, the average number of requests is 3, and the average number of returns is 3. But the other location, the average number of requests is 4, and the average number of returns is only 2. Because sometimes people pick up a car there and then bring it back at the other location. This sometimes happens in real life as well. So this means that there's an imbalance, and one location will more quickly deplete its cars than the other, and this means that you do want to sometimes ship cars from one to the other. Now we could start off with, there's a depiction of this full problem. Let me just grab that because I do have it. It should have been in the slide. I thought it was in the slide. Let's get a previous iteration. Here we go. Cheating a little bit. Oh. Doesn't want to open in the preview. Here we go. There we go. So this is the process of finding that solution using policy iteration. So we have a policy here that is depicted as a big matrix where the axes are shown there at the bottom. There's a number of cars at one location, and there's a number of cars at the other location. This is basically for the overnight, because your decision is overnight to move this many cars. And in all of these different situations you might find yourself, all these combinations of numbers, this shows how many cars to move from one location to the other. If it's a positive number, you're basically moving from one location to the other. If it's a negative number, it means you're moving them the other way. The first policy basically just says don't do anything, and we can estimate its value. And when we do, we just estimate the value of that policy, and then we pick the greedy action according to that first estimate, and that's what you get under pi1 there. And we see that an interesting policy already emerged, where we're very often shipping cars from one location to the other. The maximum amount of cars that we can ship, which was 5, we are shipping them, except if there's already a lot of cars there. If we go further along the axes, at some point you stop shipping them because there's already so many cars at the other location. This is just after one sequence of the policy iteration, but this is assuming that you basically did the full policy evaluation as an inner loop. So you found the true value of this first policy, and then you went greedy with respect to that. If you repeat that process, you can see that the policy basically becomes closer and closer to what you get at the end, which in this case is only after a few iterations. Very quickly it approaches a certain form, which I couldn't have been able to predict just by seeing the problem, but this turns out to be the optimal policy. And at some point it stops changing. You can already see that the difference between the first and the second is quite big, and then the difference becomes smaller and smaller each time you go. And then you can also look at what the value is, which is depicted there as a three-dimensional plot. For each element of your state, there's a number. So we've depicted the state here as a two-dimensional thing, the number of cars in one location, number of cars in the other location, and then the value just becomes the height of that plot. This is the value associated with the policy there at the end in denoted pi4. So the thing here to note is that this thing also in this less trivial problem converges to apparently an optimal solution, and it will be optimal. You can prove that it will be, and that the optimal solution is sometimes quite non-trivial. It's not something that you can easily reason through without doing the compute. There was a question?
So I was just going to ask you, you may already have answered this, but in this problem,
Yeah.
if you already have the maximum number of cars and someone returns one, do you just not get anything? So if you have 20 cars in a location and there are returns, does nothing happen?
I forget the details. So it might be, so the question is, what do the dynamics do when cars get returned when the location is already at its maximum?
Yeah, it seems sometimes to be fine with having 20 cars.
Yeah.
in a location.
So you could basically, there's different versions of this that you could define, right? This is basically a question about what are the exact state dynamics. And I must say I forgot. I don't know whether it just caps at 20 or whether it goes beyond 20, but only when people return, but you can't bring any to give it a beyond 20. And these are indeed two different problems, which will need maybe have slightly different solutions. And I don't remember which one this is exactly for, but the process is the same. So you could solve both of these with the same solution method, essentially.
I have a question as well.
Yeah.
Just while people are asking questions like that, why were there arrows pointing out of the box with the previous example?
Let's go back to, oh, sorry.
You could go off. Nowhere.
So we're back at the,
No, one more.
the,
At the beginning.
oh yes, so why are there arrows pointing at the boundaries here? That's because you can't tell from your value function that it's suboptimal to stay in the same state. So at the very first case, if you're in the upper right corner, let's say, each action that you take will give you a reward of 0. Now you might argue, even then it's maybe silly to stay in the same situation, because you might still know you want to escape. But actually what you did, if you do assume that, you made an assumption about the problem, which is that the rewards are generally negative. In reality, there might be a state where you get a positive reward, but only if you go to the same state again and again. And in that case, you would actually want to stay in the same state. So as far as the algorithms are concerned, they're completely indifferent to these things. We're not putting that prior knowledge in, that in this case the rewards are all negative. If you would put that prior knowledge in, for instance, one thing you could do is you could say, actually, you really never want to transition to yourself, because that's just generally a bad idea. But that's actually only true when your rewards are generally negative on that transition. If they would be able to be positive, then it might actually be the optimal thing to do. This happens as well in real problems, in bigger problems, because sometimes it's much easier for an agent, say an agent playing an Atari game, it might just learn to stand still, because it's safer to stand still than to pursue a reward that is high, but it doesn't know it exists, and it doesn't know how to get it. So this does indeed sometimes happen. You could call this a suboptimal solution, say in policy space. In dynamic programming, you're guaranteed not to find that, right? We can iterate through everything, and we can guarantee to find the optimal policy. But in the general case, where you have partial observability and all the other problems with approximations, then it can actually happen that you get stuck. It's a good question, thanks. Okay. So, by the way, I'll put in the slide that I went through the other presentation for in this one as well before I upload. So the question was, okay, so beyond policy iteration, so far we've assumed that in each of the evaluation steps of a policy, we went for the full value for the policy we were considering at that time. A question is, do you really need to do that? Because it means we basically have an inner loop. We have the outer loop of the policy iteration, which in each step redefines your policy with respect to the current values. But it has this inner loop of policy evaluation, which itself might be expensive. So there's a question, do we need that, and how much of it do we need? So for instance, should we be able to stop when we are close? Let's say our values are updating, and at some point they seem to be updating less. The difference between each iteration becomes a little bit smaller, and you might reason, maybe I'm already getting close. Maybe that's enough. Maybe you should just stop there and not have the small marginal returns of continuing. So for instance, one way to implement that is to have a threshold on the change and to stop when the threshold when your change falls below that threshold. Alternatively, you could also just say I'm going to do a certain number of iterations. I'm just going to pick a k, and I'm going to do k iterations of evaluation before I then do my policy improvement step. In the small grid world we looked at before, case 3 was already sufficient to achieve an optimal policy. This is essentially because each of the states was at most 3 steps away from the terminal states. But of course, this was only considering one step of policy iteration. If you do multiple steps of policy iteration, maybe each of these steps doesn't have to have that many policy evaluation steps. So for instance, why not update the policy on every iteration? If an iteration of policy evaluation truly moves your value towards the true values, can we not immediately use that to immediately improve our policy and then continue for the new policy rather than waiting a long time before we finally update our policy and finally start considering this new thing? Turns out this is equivalent to something called value iteration. But in order to get there, I'm actually going to do a different thing. I'm going to go back to the same way we obtained policy evaluation. I'm just going to take a Bellman equation. But instead of taking the Bellman expectation equation, I'm going to take the Bellman optimality equation, and I'm just going to turn that into an update. So, to remind ourselves, if there wasn't an arrow there but an equal sign, then we could have the value on the left-hand side be v star and the value on the right-hand side internally also be v star, and this would just be your definition of your optimal value. So a similar principle that we had for the policy evaluation case applies here, that whenever this update stops doing anything, we must have found the optimal values. But interestingly, we're not reasoning about policies here explicitly. We're just finding the optimal values basically immediately, in some sense. Now, I haven't proven that this converges, but it actually does to the optimal values. Through like a similar proof, you could do that, as I showed before. But now note that this is actually equivalent to what we were just calling policy iteration, where we just take one value estimation step and then immediately greedify. We've just written it down in one equation. The expectation there is essentially what the policy evaluation does when you do exactly one step of it. And the max A there is essentially what the policy improvement step does. It takes the greedy action with respect to the new policy. We're just doing it in one step rather than in 2. So these are equivalent. And this is an example of what happens if you do that. So this is similar to before. This is shortest path problem. But in this case, we're not evaluating, say, a random policy. We're just going to apply this value iteration idea. This algorithm is called value iteration for historical reasons. It's just what it is. So sometimes these things are a little bit hard to get in your head sticky, because again, the name is not that informative. But this is an example of applying that process, that iterative process. So, the indexing is slightly off here. What we previously called the 0th value here is called the first value. It's just indexing by 1 or indexing by 0. So we just initialized our value at v1 to be 0 everywhere. This is an arbitrary choice that we ourselves made. The value of the terminal state in the upper left corner is pegged to be at 0. By definition, terminal states have a value of 0. Your life stops at the terminal state. You cannot get more reward. It has a defined value of 0. Then when we apply value iteration, first we get a similar thing that we had for the policy evaluation case. We just get a -1 everywhere, because we've defined the reward to be -1 on each step. This is because we want to do shortest path. We want to basically get our values to be the negative amount of steps it takes for your optimal policy to get to the termination. Now at the next step, the values near the termination don't actually change anymore. They were at -1. They're still at -1. This is because we're considering the maximum action that you can take from this state. We're no longer considering just a random policy. We're looking at all of the next states, and from this state next to the terminal state, the most promising state is the terminal state, which is a value of 0. All the other states in comparison look pretty horrible, so you don't go there. So the value remains at -1, and it stays actually at that -1 throughout. And if you do a number of iterations here, you find that eventually you get these values, and when you're here, they won't change anymore. This is undiscounted, So again, the semantics now of these values are just the negative number of steps until you reach the termination. But they're no longer the negative expected steps under a random policy. These are now the actual steps you take when you take the shortest path to the terminal state, because we're using value iteration rather than policy evaluation. So this is just an intuitive way to show you that the process works, and it works more in general. And then here you could essentially stop, because you would notice if you would do that again, you would notice that your value function hasn't changed, and then by definition it means that this is then the Bellman optimality equation. Because if k plus 1, the value k plus 1 is equal to the value at k, that means they must both be v star, which means you must have found the optimal values. So it's fairly easy to check. If you just repeat this process, whenever it stops changing altogether, you found the optimal values. In general, this can take a while for big MDPs, so you might also just stop a little bit short of that and be okay with slightly suboptimal values, but still probably much better than the arbitrary values than you started off with. So we've discussed a number of methods now. Just to recap that, all of these are synchronous dynamic programming algorithms, with which I mean that so far we've just basically considered updating all of the states on each step all at the same time. When we did policy evaluation, we just update the values for all of the states. And when we do the improvement step, we just make the policy greedy in all of the states at the same time. And this is sometimes called synchronous, because we're doing a synchronous update across states. Now for the prediction case, if we just want to do policy evaluation, the associated Bellman equation is the Bellman expectation equation, which doesn't have a max. And the algorithm we can use for that is policy evaluation. And we can iterate. So you could call that iterative policy evaluation. Maybe the problem, you could also say, is policy evaluation rather than prediction. And then the algorithm is the dynamic programming iterative policy evaluation. For the problem of control, which is a shorthand for saying the problem of finding the optimal policy, we can again use the Bellman expectation equation to do policy evaluation with, or the iterative version thereof. And then we could greedify after each time we found a better value. We've discussed that we can do that waiting all the way till the end. We could fully evaluate a policy and then greedify, or you could stop earlier and then greedify. This process is called policy iteration. If we want to do control, we could also stop short after exactly one step of policy evaluation before we then improve our policy. And this process is called value iteration. And the associated Bellman equation is the Bellman optimality equation, because value iteration can also be considered just turning that equation into an update. Now these algorithms can be based on state value functions, as we mostly discussed. And then the complexity is of order number of actions times the number of states squared. One way to understand that is that there's this transition matrix, which goes from states to states, which is therefore number of states by number of states. So it's number of states squared, in order to do each time one of these next steps. Another way to say the same thing, to understand why this is order of states squared, or order of number of states squared, is that for each state we have to consider the possibilities of ending up in each of the other states. Now of course in practice there might be MDPs in which you don't necessarily have to consider all of them, so there might be in practice cases where you can maybe mitigate the compute, do it slightly cheaper, but in general this is the compute you need. You can apply the same principle to state action value functions, in which case the complexity becomes slightly higher because you have to do this for each action now, rather than in addition to the number of states. You're just also essentially storing more stuff. You have estimates for states and action pairs now, rather than just state values. Now the number of states is more typically the bigger number, so the difference between those two things is typically not that big a concern. The larger concern is that if your number of states is big, then this squared might be too big to fit in memory. If you have 1,000,000 states, 1,000,000 squared is already a pretty big number. You don't want to necessarily consider all of them. So there's a solution or a partial solution to that, which is to not do everything. This kind of sounds like a sensible thing. Maybe you don't want to consider all of the states, all of them at the same time. And this can be done, and this is a sound idea. And there's different ways you can do this, and I'll discuss a couple. So this in general is called asynchronous dynamic programming, which essentially just means we're considering maybe one state at a time or a couple of states at a time rather than everything at the same time in parallel always. And this can significantly reduce the actual compute you use. This is still guaranteed to converge under the same conditions as the synchronous dynamic programming is essentially guaranteed if you do continue to update everything. So for state value functions, you do need to consider all states basically often enough in total at the end. Doesn't mean you have to consider all of them at the same time, but you just have to eventually get to them back and do some updates. Now I'll just discuss 3 simple ideas for asynchronous dynamic programming. These are probably fairly intuitive. First one is in place, which is kind of a simple idea that you could do the updates maybe slightly faster than we were doing before by avoiding storing 2 copies. So essentially what we did before, we had a new value, which was defined in terms of the old values, and we would essentially assign these things, but note that the state that we're bootstrapping on, the state that we're evaluating as the old value, might be one for which we already have a new value, because we already computed that. If we don't actually do them in parallel, but we just go through all the states, there's going to be one state that you've done first. So the idea is very simple, that whenever you consider a state, you just immediately overwrite that value, and then you use that. It makes the notation slightly more complex, because before we had a v at iteration k, and then we considered updating all of them to the v at iteration k plus 1, and we knew that for all of them they were using the v at iteration k as their state estimate. In this case, there would actually be all these intermediate versions. Things you've already updated, things you haven't yet updated. But whenever you start updating something, you'll just use the most recent values, and this should just be faster, and it is. So it's a simple trick, but it does speed up your compute. In this case, we're still doing a full sweep across the states, so this is still a little bit synchronous in some sense. It's a little bit compute intensive. So another thing we could do is we could pick specific states to update. And one idea here is to use the magnitude of the error. We're essentially going to update the states that were most wrong in the past. So you could essentially keep the thing here on the left, this max A expected reward plus discounted next value. This is the target for a value iteration update. So you could take that from your previous iteration, because we might be doing the in-place stuff. I didn't actually index them with k's or k minus 1s, but you might just consider what was the size of the update I did in the past for this specific state S, and then we just store that somewhere. And if the update was big, essentially we'll return to this quickly. We'll try it again, because we think maybe there was a lot to learn. If for this specific state there was basically no update, we might assume maybe that value is already quite accurate. Maybe let's not consider it that quickly again. And this is called prioritized sweeping, because we're still sweeping across the state space, but we're doing it with a priority, which in this case is given by the previous update. There's different ways to prioritize. You can come up with your own ways to prioritize as well. Another way, which came up in the first lecture as well, somebody mentioned, why don't you just start at the end and then go backwards? And that's indeed also a valid algorithm. You could start at the end and then go backwards, because then you're always bootstrapping on things you've already updated, which is also a good idea. This is in some sense similar to the idea of prioritizing, except here we're giving a different measure. And this can be implemented quite efficiently, by the way, by using a priority queue. There's just ways to do that. And finally, one thing that you could also consider is to focus your compute even more on the things that matter. And this is especially relevant if you have an actual agent that is moving around in this MDP, and this agent will be in a certain state. And if that's the case, maybe you mostly care about getting the values at the next states that you use to pick your action, to have those be accurate. So if you're in a certain state and you have a little bit of time to think, maybe you want to spend that time to update the values that are of interest to you right now, rather than values that might eventually be of interest to you. Because it might be the case that there are states that you're never going to return to, for instance. And then why would you ever use any compute to update those? Maybe you just don't want to do that. So this is sometimes called real-time dynamic programming. The idea is, again, somewhat similar to the prioritized sweeping, where we just basically picked a different priority. We are now prioritizing in some sense by closeness to where we are, rather than how big the update was previously. But otherwise, you could use similar ideas. And this, again, can very much limit the amount of states that you actually update, and therefore very much limit your compute. Now, one way to think about dynamic programming, and this is especially useful to contrast it later, is to basically go back just to the, just think of the synchronous case for simplicity. But for each state, dynamic programming will consider all of the possible actions, and then for each state action pair, it will consider all of the possible outcomes. This is sometimes called a full width backup, because we're using the full width of the tree, even if we're only using one step in terms of depth. This works, and it's convergent, and it's you can get it to be fairly efficient, but it only works up to, say, medium-sized problems, where maybe you have millions of states. Now, obviously, we can't do the synchronous dynamic programming with millions of states unless you have a lot of compute. But if you do the asynchronous things, you can get pretty good solutions for millions of states, and people have done this in practice, which is actually quite impressive, because with millions of states, you can model quite interesting and complex problems. Some cases will still not be enough. If your input, say, is a video stream, and you also want to maybe remember a few pictures from the past, because otherwise it's too non-Markovian, then the amounts of ways you can cut that up are, even if you do fairly coarse cutoff, say in the intensity of each pixel, you easily get more than millions of frames. Millions of states that you could investigate. So then we need different solutions, which we'll talk about in this course as well. But if you can write down an MDP which is only, say, thousands or tens of thousands of states, then you can apply modern dynamic programming methods on modern machines quite easily, and you can fully solve them. For larger problems, and maybe the best way to say that is to say that dynamic programming suffers the curse of dimensionality. This is a term that also originated from Richard Bellman, which essentially means if your problem has more than one dimension, the amounts of states in your problem will very quickly grow. And one way to think about that is that in the car dealership, for instance, we've only considered how many cars there were at one situation, one location, and at the other. But you could add a dimension, say the weather. And if the weather can only, say, take 3 different states, it already means that we're multiplying the number of states by 3. If there's yet another dimension, say time of year, let's say month, and there's yet another 12 different possible situations that can happen across this dimension, we're again multiplying the amount of states with the number 12. So this means that each time you add a dimension to your problem, the amount of states gets multiplied by the number of elements in that dimension, in a sense. There's a continuous version of this as well, of course, and this just means that things very quickly get unwieldy, and it's very easy to get systems that actually need more than millions of states if you don't have a lot of prior knowledge of how to cut up and how to define your state space. In addition, there's problems with loads of actions as well. That's another thing to consider that we really didn't touch much upon, which can also make the compute grow high. So one other thing that we'll touch upon in depth, but we can start talking about a little bit, is to apply the ideas we've, of course, learned from the other side of the course, to use function approximation. And the idea is, of course, quite simple there, where we're basically just going to say, we have a value function. This is going to be a parametric function. Let's say it's a deep neural network. And we're going to use that instead of enumerating all of these states. There's many benefits of this. One benefit is it can deal maybe with larger state spaces. But another benefit is that it's much easier maybe to generalize. That's something we haven't really considered. So far we've considered separate states. But states might be very similar. And you might want to exploit that. Deep networks and other function approximators have the natural tendency to generalize similar states, to already give you an estimate, even if you've never seen this specific state, just by generalizing things you have seen which are kind of similar in some sense. But we can abstract away which function approximation we're using here, but we're just going to say it's some parametric function approximation, and we're going to denote the parameter vector theta, which you can think of as being, say, for instance, the weights in your deep neural network. And then we have an estimate value function, and how do we then update this? Well, we can use the same ideas as before. We could, for instance, do asynchronous dynamic programming. So we just pick a couple of states. Maybe we do have a full model that we can reason through. Maybe there's not too many actions, so we can actually consider all of the possible actions. And what we could then do is just pick a few sample states. This is the asynchronous part. And for each of these sample states, we can compute a target using just, for instance, value iteration in this case. We do the one-step look ahead. Of course, this assumes that you can do the one-step look ahead with either a true model or maybe a very good learned model. But let's assume the true model for now. But then maybe we can find a new parameter vector by simply minimizing the difference between our current estimates and this target. And one way to do that in practice would be, for instance, you don't fully minimize, but you just take one step. Other things people have done is to consider linear function approximation, in which case sometimes you can just solve these things rather than doing a gradient step. But in general, there's many ways to minimize this loss slowly. And this turns out to also be a sound algorithm. You can use this on real problems. You could also use this, as we'll see later, if you don't have a true model, by sampling. And this turns out to work in practice as well, and in large problems. So I already mentioned this a couple of times, but it's good to be explicit about this. Dynamic programming improves the estimate of a value at a certain state. But in order to do that, it uses the estimate of the value at the next state. The same estimate, essentially. The same value function that you're optimizing, you're also using. This is sometimes called learning a guess from a guess. And this is a very core idea to reinforcement learning. It's not immediately clear that this is sound, that this is a good thing to do. We've shown for at least simple cases, and we've just mentioned for other cases, that indeed in dynamic programming this works. But what if your value functions are even more approximate because they're just some function approximation, some deep neural network that might be arbitrarily wrong, say, in certain states? Does it still work? Is it a sound idea? Well, in some cases we can really say it's sound. We can say this converges, even if we don't have a true model, and we'll touch upon that later. In other cases we can't go that far. For instance, if we have a very highly nonlinear function, we might not be able to say exactly where it goes, but we can still see that in practice it does work on big problems. And we'll discuss algorithms to use that. There is a theoretical danger of divergence, which means that your parameters go off into basically la-la land when combining the bootstrapping with general function approximation, even with linear functions. But this happens when you learn things, what is sometimes called off policy, and I'll use that phrase more often later in later lectures. But it means when you don't appreciate the actual transitions in terms of where they lead you, in terms of your policy. This theoretical danger is rarely encountered in practice, but there's very small toy problems, and this gives one, in which you can show that this is a problem. Now, I don't have time to step through this completely, but just to give you, just to tell you what we're looking at here, there's two states, and we have a function approximator that only has one parameter. And we're basically saying the value of the first state will be theta, which is just your parameter, and the value of the second state, your estimate of the value of the second state, will be 2 theta. The rewards are 0 everywhere, so we know that the true value is actually in the span of this function. You should just set theta to 0 and you're done. But turns out, if your theta is not initially 0, and the probability of this loop happening is also non-zero, then if you update both of these states at the same time, you do the synchronous dynamic programming-like idea, and you just use this update where we fully minimize the loss each time for theta. Turns out this diverges. Theta just goes off into infinity. And the reason is that we're not appreciating the fact that you're actually, if you would step through this problem, you would spend more time in the second state. And if you take care of that, if you are aware of that in your update, so you update that state more often than the first state as well, then everything's fine. But if you just update both of them at the same rate, turns out theta goes off into la-la land, essentially. Okay, so that's all the time. This is still relevant, but maybe it should go on Moodle. I don't know whether people are kicking us out. Seems to be okay. If we do need to leave the room, I'll be available just outside if somebody still has questions. Thank you.